Welcome, everybody. Thanks for coming out and spending a little bit of your evening with us. We really appreciate it, and we hope to make it worthwhile. My name is Victor Krabbendam. I am the Project Manager for LSST, and have been at this job for the last 14 years. This is how much time we've spent designing, developing, and getting to this stage of construction. And so you can imagine that myself and many of my colleagues that have been here for a while trying to make this a reality are quite excited to get this project to the state that we're in right now. We hope to convey some of that to you tonight. By show of hands, how many people are at their first LSST talk? Oh. Well, to you, we really hope to convey our excitement. This is great. And so there's an awful lot of activity happening here on LSST in Tucson. Not all of it are direct staff members. We've got a lot of contractors, a lot of work going on at the U of A. How many people are in that situation? How many people are here from the U of A, have worked on some element of LSST and over the many years? So there's a few of you. Thank you very much. This is all part of your efforts as well. We really appreciate what you've done to make LSST a reality. So, welcome again. What you can see here on the screen is that during this particular week, we have over 300 people here in the LSST family at this resort, spending their time collaborating on the remainders of the design work, on the remaining construction activities, getting ready for testing, getting ready for the commissioning activities, and for planning operations, all in an effort to make sure that we get the absolute most and maximize the value of what we're about to build and what the survey is about to bring to not just scientists, but the community in general. So before I go too far, because many of you are new, let me just make sure we all understand each other about what is LSST. LSST is more than just a telescope. Our mission is to construct an observing facility, to conduct a 10-year optical survey where we look at the sky, the whole sky that is visible to us from our site, and then process all the data that we take, develop all that data into archives, and preserve it to both scientists and the community alike. And to do that, what we have to do is build an 8.4 meter class telescope. That to us it's a 27-foot primary mirror in diameter. So that's the size of the main collecting aperture of the telescope. We also have to add to that a huge 3.2 gigapixel camera. And we'll show you an image of that in a moment. And then combined with those two observing aspects, we have to add to it a petabyte scale data management facility. That's a huge computing facility to both store data and analyze all of that data to make these products. And so part of that as well is it doesn't do any good to only make the data and put it into big computers. We also have to develop the portal and the interfaces for both our professional scientists and for our public enthusiasts and for educators alike to be able to get access to that data. And so that's what LSST is in a simple idea. So how are we funded? We are a public-private partnership, and the National Science Foundation has contributed or is funding us at $473 million. Add to that $168 million that comes from the Department of Energy. And early on in the development period, remember I said 14 years ago? Well, early on in that development period, we had a lot of private donors and corporate donors, institutional donors that were part of LSST Corporation, which is a 501c3 corporation right here in Arizona. And that money was really instrumental in getting us started in the early stages of the project. So that all combined is what is making it possible for us to build the facility that we are building. In the next few slides, what I want to point out to you is that this project is being executed by a very large global team. And I'll flip through these, and this basically is a slide per every sort of major element of the project. And so you can see those boxes on the right. There's one for project management and engineering, that's one team. There's a team for data management. There's a team for camera. There's a team for the telescope and site aspects. And then there's a team to build the education, public outreach, instrumentation in that system. And so as we go through that, what I also want you to point out is if it's blue, it's basically people, staff members on the team. If it's purple, it's one of our major contractors. The other thing to point out is, look how many times Tucson shows up in every element of the project. We're pointing to Tucson frequently. And we're also pointing down south in central Chile. I didn't mention, that's where we're building this telescope. Also, if you look into where you would point to is about central Illinois, is where we're going to put our LSST data facility. That's where all of the data is going from Chile all the way up to NCSA in Illinois, and also a sister computing center over in France. So those are the two primary locations where we will take this data and process it and turn it into the data products. So we keep flipping through, and I go to the camera team. You can see again, Tucson is in this list. You can see a sort of combination of staff and contracted efforts. In this particular case, that $168 million that's coming from the Department of Energy is strongly focused on just building that camera, and that is primarily being done out of the Department of Energy National Labs. Now we go to the telescope on site. Now you can start to see this. The arrows are pointing us strongly to Tucson and to central Chile where the site is located. Also, you see a lot of purple. The telescope is being built in lots of big contracted efforts. And then finally, education public outreach. Here too, the team has a very strong international diversity in making sure that we build a system that really reaches out to the most people that we can. So last year, my colleague Chuck Claver and I did a talk. It was a little bit more on some of the history, some of the motivation, and then also the status. And that talk is still available to you if you point your browser to YouTube and you type in LSST 2017, you'll get this talk, and you'll get a lovely recording of myself and Chuck doing that talk. But also, if you go to there, you'll end up on the LSST channel of YouTube. And there is an immense set of resources there, many videos, day-in-the-life slideshows, lots of really interesting insights into what it has taken to get to the project to this point in time. So I really encourage you to spend a moment and look at that. So the other thing I really wanted to do, particularly since people like myself have been doing this so long and shown pictures of designs and renderings, and what's really important to us is that we're so far beyond that. And so for the next few slides, I just want to make sure that I preface the following speakers with really getting the point across that we are way beyond designs. And so here's a classic example. There's a rendering of what we thought the building was going to look like on the mountaintop back in 2012. And what you see on the top left is a photo taken just a couple months ago. So this is just an example of what's happening all across the project. In every element, we're taking designs into actual hardware. Another good example of that is what happened here in Tucson with our colleagues at the University of Arizona, now called the Richard Karras Mirror Lab. They took 17 tons of raw glass and formed it into one single very large complex mirror. That mirror has two reflective surfaces, and so by the time they were done manufacturing this very unique two-surface single mirror piece of glass, they had both of those surfaces accurate to less than the thickness of a hair. That was done in 2014, primarily from that early funding that we got from private donations. We were able to move that and stuck it in storage at the Tucson International Airport where it sits today. What we expect to do now is take it back out of there, bring it back to the Mirror Lab, and test it one more time, and then send it off to Chile, and we hope to have it there by June of next year. So why has it been sitting there for 3 years? Well, it turns out that as complex as that mirror is to build, it's not enough yet. We have to support that mirror to make a proper assembly. And so what we spent the last 3 years doing was building the structural elements, the electromechanical elements, the pneumatic elements, all the computer and electrical parts that is required to make this an actual mirror system. And so now that those parts have been assembled through a combination of our own staff and members of the Cade Industries team in South Tucson, we now have all of that hardware built and tested. And if you look at the picture on the right, it doesn't really identify itself well, but the turquoise part is the actual steel structure that holds up the mirror, and the rather brown-looking, rusty-looking element is an exact replica in steel of the mirror itself. That enables us to do this system testing. So if I think about those, we think about the glass, that's great. Now you can see this picture it's hard to get an image of it, but this is in the background, those two surfaces of the primary mirror, and in the foreground is our secondary mirror, and you'll see some images later from Phil about how the optical design works. But to make a telescope, you've got to take these optics, you have to hold them close together and keep them stable, and then you have to point it across the sky. And so what we need is a very stiff, large structure which becomes a telescope that we all can envision when we think about looking at a telescope. This particular one is extremely stiff because we move it very fast across the sky to really take advantage of and get as many images of the sky as we can to add to our database. So this is a massive structure, and this also is not just a design. And so what you see here is the actual telescope pre-assembled at the factory in Spain under test. And so this is as real as it gets until it gets to the summit. And so these, in fact, this particular video is only a week old. So if we move on to this camera, this is a massive camera. These are sort of three really key elements of the camera it's essentially its size. If you look at the scale in the very front on the far left, you see a silhouette of a person to demonstrate 5'5". That's the entrance window of this camera. So if the camera were sitting here on this stage with me, I'd be standing here, put my arm up on top of it. And it would extend out beyond that. The other key thing here is that the red element is where the actual sensors are. That's what we call the cryostat. And there's an awful lot of electronics, a lot of utilities required to support the sensors in that cryostat. And it's really tight. Because of where it sits in the telescope, it has to be tight, it has to be all very close and confined. And so even with those tight constraints, we're still able to carry 5 filters, and each filter is roughly a manhole cover. And so those 5 filters are sitting in there, and if you look at the picture on the right, that's an image of a full-size mock-up or pre-assembled version of the filter mechanism that's required to handle these massive filters and keep them in the camera ready to be used and put them in front of the aperture. The other part of it is, where are the sensors? And these sensors are extremely fragile, and what it takes to support them, the image on the far right is an image looking into the front of the cryostat if you were looking through the last lens, and this particular image shows that the cryostat is ready for us to start inserting parts of the focal plane. So what does that focal plane look like? Looks a lot like this. We start with a single sensor, which is basically an inch square. We call a 4K by 4K device. We take 9 of those, assemble them into what we call a raft. That's shown there in the middle of the screen. And we take 21 of those rafts and we assemble that up into what becomes the single focal plane, sort of imaged on the left there, with one of those rafts still sticking out a little bit. Just to show you that it's also much further along than just designs, the image on the right is a photograph of the front of one of those rafts with the sensors in this pretty blue reflective reflection in the image. So if you're familiar with astronomical cameras, it's probably not going to be, you'll certainly understand that there's many a camera that has been delayed because of sensors. Sensors are difficult to fabricate, they're very sensitive, it's almost an art form. But what we're happy about is that we conducted this process by contracting with 2 individual vendors, and we have already gotten 264 sensors that we need to build this focal plane. And we only need 208, so now the final deliveries are really just about picking the best of the batch. We send all of those to our colleagues in Brookhaven National Labs in Long Island, and they are the ones that assemble those into rafts. They have already assembled 12 of these nine sensor rafts, so we essentially have half of the sensors ready for installation into the camera. Another thing I'll point out is that one of the 2 vendors that we got all these sensors from is the University of Arizona Imaging Technology Lab, right here in Tucson. Another part that I mentioned about the camera is the sheer size. And so the also difficult elements of all of these telescopes is these large optics. They're very precise, they're very large. And I'm also happy to say that these two elements have been completed. Ball Aerospace was responsible for the L1, L2 assembly. Their partner was Arizona Optical Systems right here in Tucson. Arizona Optical has completed those two elements. L2, in fact, shown there on the bottom left, is already coated in the France facility, and L1 awaits its opportunity for the same. Finally, there is hardware everywhere at this point in LSST, and on the right is just another example of hardware that's already made it to the site. It's a small 1.2 meter atmospheric calibration telescope that was refurbished from an older version, from an old telescope we got off of Kitt Peak by Astronomical Consultants and Equipment, also from here in Tucson. And so they have already finished that refurbishment, have already installed it on the summit. So these are just some examples, and I've chose examples that obviously are quite Tucson-based, but again, LSST is a global enterprise, and the team building all of the assets are really quite internationally diverse. Finally, on the right, in the bottom right, you see a coating chamber. It's not shown, you can't see scale very well unless you happen to know what a scissors lift size is, but that's also that holds the 27-foot mirror for coatings. That too was built in Germany and is already on its way, as you can see in the image in the middle, being shipped from, that's a barge going from Germany to Belgium and is on its way basically to the summit. We are quite far along. LSST is on track to be getting to first light in 2021 and start the survey in 2022. So I pulled out my little cheat sheet because what I really want to do at this point is properly introduce the two speakers, the real two speakers for the night. And the first one is going to be Phil Marshall. And Phil is a staff scientist, and this is the hard part for me, the Kavli Institute for Particle Astrophysics and Cosmology at the SLAC National Accelerator Laboratory. I always get that mixed up too. And so Phil is going to talk to you about some of the science mission of LSST and really some of the engagement, because he is also a member of the LSST Dark Energy Collaboration, and his science interest is really in observational cosmology using gravitational lensing. He likes the idea of weighing galaxies and really trying to measure the expansion of the universe using this lensing effects. Following Phil, we have Ardis Herrold, and she's going to come up, and she is a nationally recognized education specialist in science and has many years of classroom experience. She's been the president of the National Earth Sciences Teachers Association. She's received the Brennan Award for high school astronomy teachers. She's pioneered efforts to include students in authentic research, and that's authentic research with federal research programs and assets that are ground-based, that are space-based, and now we're really happy to have her on our team to bring all of that experience to LSST. So at this point, let me invite Phil to come on up.
Thanks, Victor. All right, good evening, everyone. Nice to see you all. Let's see if I can make this work. All right, so exploring the final frontier with the Large Synoptic Survey Telescope, with the title we chose. Space, as you know, the final frontier. Carl Sagan used to like to say the frontier is everywhere. And certainly one thing I enjoy about astronomy is the way you can invite people to join you to sort of close to the cutting edge of research just by taking them outside to look at the night sky. Perhaps you've been enjoying the Perseids this week. I intend to later in the swimming pool. Okay, so the final frontier, we were thinking about this talk and how we'd approach it, making links between the kinds of things that scientists do, professional scientists like me, and the kinds of things that Ardis is planning to do with LSST, which she'll get to in the second half. But it reminded me of a funny conversation I'd had with my wife, actually, on the third or fourth date. She was asking me what I do and why I do it, and so I was explaining a bit about being curious, being a scientist, working on this telescope and getting to think about questions like, where did we come from? And how does the universe work? That's probably my favorite one. And what else is out there? And she wanted to know, why do we do this? I was saying that basically it's because we're interested and because everyone else is interested too. You like to hear about this stuff. And she said, oh, you're an explorer. You're like Magellan. She's a romantic. So here's Ferdinand Magellan, who's an explorer in the 16th century. His question was, is there a way to reach the Philippines by sailing to the west? And so he put together a proposal, a familiar activity for us, and said that he wanted to do a westward voyage, and he got funding to do this trip. It took them 2 years to put together the discovery machine that they were going to use to do this exploration. It was a ship called the Victoria. He put together a crew to operate this thing, 273 people, and they set sail in 1519, 2 years after the proposal. And then 3 years after that, 18 of them came back. And Magellan didn't make it. He was killed in the Philippines on the way. So we shouldn't take this analogy too seriously, I think, hopefully. Okay, so what did Magellan and his crew discover? Magellan was there for the discovery. Basically, the main result of this investigation was the Straits of Magellan down at the tip of South America. They managed to find a way through this complicated strait into the Pacific Ocean beyond, and were then able to set sail across and make it to the Philippines. So they came back to Spain, and they were able to pass on the ship's logs, and Diego Rivero made a map based on that, and here it is. You can see the outline overlaid on top of the modern map. You can see they did pretty well. There were some blank parts. They didn't bother to go up any rest of the coast up here. They just set out across here. But he came back with the map. Now people knew how to get to the Pacific and how big the Pacific was. So imagine being there in the 1520s, and you own a ship, and now you've seen this map. Think of that whole ocean of possibility, things you can do next. So explorers make maps for others to follow. Here are some modern maps. It's data on the left, an image of the Bay Area. The map is on the right. Right? It's a simplified representation of the data, and it helps us understand what's out there in the wilds of Highway 101. And maps reveal paths forward that we may not have realized were there. So mapping is an extremely important activity to do. It's one of the key things that explorers do. Okay, so here's our discovery machine. It's not a ship for us to set sail in. It's an observatory that consists of a telescope with a camera, like Victor showed you, that's coupled to a data facility, all of which will come together to give us the ability to make new maps. So let's take a look at a little bit more about the properties of LSST. We saw a little bit from Victor about the mirror made here in Tucson. The good thing about the mirror is it's big. You can collect a lot of light with a mirror that's 8.4 meters across. And coupled to a huge camera like the one that we're building at SLAC, makes the telescope extremely fast at imaging the sky. That's the main property of LSST, is it's fast. I couldn't resist putting this in. This is me as a younger man. Not much younger. This was in 2009, the first time I visited Tucson, and I made sure that when I came, I went to the mirror lab to see the LSST mirror. And sure enough, fantastic. Okay, so LSST survey, what will it be? It's a 10-year log, like a ship's log, of half the sky. So what we'll do with LSST, when it's installed down at Chile, we'll do a survey over 10 years of the entire southern sky. The details being worked out at meetings like this and others over the next few years. But over that 10-year period, we'll take an image every 40 seconds or so, every night for those 10 years. And the result of all of that will be a movie of the southern sky, an 825-frame movie in 6 filters. I call it Technicolor for fun, of every object that's in the sky down there, all the stars and all the galaxies. It's an amazing resource. Okay, so just to give you some idea of what the LSST imaging will be like, I'm going to show you some images taken with present-day telescopes, but just to give you a sense of scale. Okay, so here you are. Imagine looking up at the full moon. You never see the full moon this big. You think you do, but you don't really. The full moon is as big as your little finger when you're at arm's length. So imagine that. And now let's look at the stars and the galaxies that you can see in a patch of sky the size of the full moon, but with a big telescope at a dark site. So here we are. This is what the night sky looks like. This is from a telescope called the Canada-France-Hawaii telescope. And the image quality is not very different from what we'll get with LSST. The depth is pretty similar too. So what you see here are lots of stars. They're the blue things with sort of cross shapes down in the middle. But you can see also a galaxy down here. It's quite a nearby galaxy. So now let's zoom in a bit. Remember, this is the size of your little finger at arm's length. And this is a hair held up at arm's length. Okay, so here's a zoom in. This is one of the types of objects that I'm most interested in. It's a gravitational lens. It's a couple of massive galaxies that look red with blue arcs around it. They're background galaxies that have been distorted by the mass in the foreground. And you can see that this is this type of object, all the galaxies actually that we see out there in the distant universe, smaller than the width of a hair at arm's length. So it's easy to image a lot of the sky at once. You can do it with your cell phone. What's difficult is to take large images of the sky at high resolution. So that's what LSST will do. Okay, so here's the footprint of the camera. This is what a picture of the night sky taken with an LSST might look like. And you can see the sensors overlaid here. To get that high resolution, we have a lot of pixels. I said it was a 3 and a bit gigapixel camera. Field of view is 60,000 pixels across. So to print that out, if you're old-fashioned like me, if you wanted to print out at 72 dots per inch, you would need a 70 by 70 foot piece of paper, and then 3 tennis courts to lay it out on. So this is going to lead to a huge data set. We're talking about billions of objects, billions of stars, billions of galaxies. And because we're going to revisit each patch of sky 825 times over 10 years, that means we'll make trillions of measurements. We won't do it by hand with rulers and things. We have computers to do it for us, so automatic measurements of all those stars and galaxies. And then we'll make all of those. That's what they'll be doing at the data facility. And the output of that will be something we call a catalog. There won't be pictures of people wearing clothes in this catalog. Each item in the catalog will be a star or a galaxy and all the properties that we've automatically measured. So the brightness, the position, the shape, and so on. And what astronomers like me will see, really, is this database. And so what we're doing now is starting to write the software to observe that database. We're building datascopes. Okay, so what can we do with this huge database? We can do a lot of science. So here's something we can do. We can take a census of the solar system. In those images, in that catalog, in that database, there'll be lots of moving objects. And because we continuously re-image the sky, we can see things move across the sky. So asteroids move, near-Earth objects, Kuiper belt objects. We'll see them in very large numbers as they move across the sky and end up in our database. So here's an interesting thing we might try and study. I don't know if you know this, but the orientations and spins of the planets in the solar system are not quite aligned with each other, as you might expect. They're a bit crooked. And so we might ask why. Turns out also that some of the objects in the Kuiper belt at the edge of the solar system have weird orbits. And they're all kind of aligned in strange ways. And it turns out you can explain all of that if there's an additional planet that's way out there, and we haven't seen it yet, Planet 9. With LSST, we'll see thousands of Kuiper belt objects. We can measure their orbits and get a very precise indication of where this planet might be. We can map out the outer regions of the solar system. We can also map the Milky Way. So the details of where all the stars are in the Milky Way tell us a lot about the Milky Way's history. How we get that knowledge is we make computer models of the Milky Way forming, or galaxies like the Milky Way forming, and we look at where the stars end up in those models, and then go and compare it to where the actual stars are in the galaxy. And the way we'll do that with LSST is we'll be matching the positions and brightnesses and colors and so on in the database with the model stars in the computer simulations. So on the right here, you see an example of a simulated Milky Way. Doesn't look much like a galaxy, does it? That's because they've zoomed in and to highlight all the streams of stars that get formed when other galaxies fall into our own. And we'll be able to see lots of streams like that with LSST. Here's a map with the present-day survey telescope, the Sloan Digital Sky Survey from the Sloan telescope. That's the picture on the left, and you can see we already know about some streams in the night sky, streams of stars. On the right-hand side, there's a computer model of how these streams come about. And in the top right, you can see that maybe we might see streams that have little kinks in them. And one of the things that can cause those kinks is a massive object flying through the stream at some point. And that massive object could be something without any stars. It could be a clump of dark matter. And so by looking at streams and the kinks in them, we can infer how much dark matter is out there in the form of small clumps and start to understand maybe what dark matter is. Okay, there's more than just our galaxy, of course, billions of galaxies. Here's from a simulation, a map of a few million galaxies. You can see that they arrange themselves in clusters, falling together under gravity as they form. And so we can expect to make maps like this of the galaxies visible in the night sky. We can also use gravitational lensing to say something about the dark matter in between these galaxies. So with the lensing effect, we can look at background galaxies, see how they're distorted as the light from those background galaxies travels through the clumpy universe and gets deflected, distorted by the mass along the line of sight. And from that, we can infer where the dark matter is and try and make maps like this one that show the filaments and clumps of where the dark matter is. We can even do that not just for all the mass out to where the background galaxies are, but we can use the colors of galaxies to say, well, what about the massive galaxies here and here and here further back, and start to build up a three-dimensional map of where the dark matter is. And so here's a little picture showing how, as the universe expands and evolves, the structures in it are falling together under gravity, and so they're getting more and more better and better defined as time goes on. And so as we look out in the universe to more and more distant galaxies, we can see back in time to see how the structures grew. So why is that important? Turns out that's one of the key pieces of information we can use to understand the expansion of the universe as a whole. So here's a picture of the universe. Actually, it's a picture of a piece of the universe. The way to understand this picture is a cross-section through this tube is like a slice, a circular slice through the universe with galaxies in it. And then arrange those slices next to each other, going back in time towards the Big Bang. So this is a picture showing you how structure is forming in the universe. So I'll try and point out some things. Here we have the Big Bang back here, and then the light left over from the Big Bang, that's the cosmic microwave background here. And then stars start to form at this time, about 400 million years after the Big Bang. And then we've got galaxies forming and falling together to make denser and more complicated structures until eventually here we are in the present day. So imagine sitting here with the LSST looking back in time, out in distance this way. Okay, so that's what we think is going on with our universe. And in particular, an interesting thing happens here. You see how this little bit of curvature here, that's supposed to represent the expanding universe accelerating, the expansion getting faster rather than slower. So we weren't expecting that. What we thought was happening was the universe was expanding, but it was full of heavy things like galaxies that would eventually pull it all back together under gravity so that the universe's expansion would stop one day and then start to reverse and sort of collapse back in on itself so that the universe would end in a big crunch. That's what we used to think was going to happen. But we don't think that anymore. Turns out that's not what the universe is doing at all. The expansion's getting faster and faster. So this was a shock. It's a bit like being told all your life that what goes up must come down. So the expansion of the universe is accelerating, and no one knows why. This is one of the biggest mysteries in all of science. And so with LSST, we're setting out to try and tackle this, to make better and better maps to help inform what's going on. What is the cause of this accelerated expansion? So, we're in the business of measuring acceleration as best we can. Try and make a very precise measurement of the expansion of the universe, this acceleration, in order to say what could be going on and also rule out some ideas for what could be going on. So we need to measure cosmic acceleration to something around 1% precision. So if you think about it, acceleration, when do you feel acceleration? It's when you're falling, or if you're on a plane or in a car and you accelerate forwards and you fall backwards. So being on a slope and feeling gravity is equivalent to accelerating. So thinking about measuring acceleration is like thinking about measuring gradients, grades on a road. So if we look at this picture, this is from San Francisco. You can see that there's a grade in the background, and we should think, well, how would we measure the slope of this road? How are we going to measure the acceleration that we would feel if we were on that slope? So basically, there's two ways we can do this. One is we can roll objects down the slope and see how much faster they get. That's one way. Look at the dynamics of falling objects. And so galaxies and dark matter halos clustering together, those are falling objects, and those dynamics tell us about the acceleration. We can do another thing. We can compare how high up these cars in this case are compared to how far away they are. So the elevation is easy. We can just see it. The distance is harder, right? We don't know how far away they are or how big a block is. So measuring distance in the universe is what we need to do. And we can do that with things called standard candles. And very good standard candles are these type 1a supernovae. So type 1a supernova happens when a white dwarf is in a binary system with a regular star. When that star gets old, uses up its fuel, puffs up into a red giant, starts to lose gas onto the white dwarf, until eventually the white dwarf reaches a critical mass and it can't support itself anymore, collapses and explodes. And it always happens at the same mass threshold, so type 1a supernovae end up looking roughly the same. Because they look roughly the same, if you see one here and measure its brightness, you know how far away it is. If you see one here, it will be dimmer by an amount that you already know. So you can use supernovae to measure distance in the universe. We know how fast they seem to be moving away from us, from their color, or from the color of their host galaxies. So we can figure out something about the expansion of the universe. That way we can measure the acceleration that way. So with LSST, we'll see several thousand of these per night, and about 100,000 over the 10 years. And we can use that to make very accurate measurement of the expansion of the universe. If you think about it, we can do it over the whole of the southern sky. So we could ask questions like, well, is the acceleration of the expansion of the universe the same in this direction as in this direction? Questions that we haven't been able to answer yet. Okay, so how well do we think we can do here in the Dark Energy Science Collaboration? Here's a new picture that we made just this year. This is a forecast for our uncertainty after 10 years in two parameters that describe this new law of physics about the thing that drives the accelerating expansion of the universe. We don't know what's going on. We don't have a good model for it, and so we give it a name. It's called dark energy. We imagine that there's this mysterious thing that causes the expansion, and then we can ask, well, how well could we measure that thing with LSST? So LSST gives us 5 ways of measuring either distance in the universe or the growth of structure in the universe. We combine them all together, and we think we can get to about 1% precision. We require of ourselves 2% precision, but we're ambitious people, so we're going to aim for 1%. Okay, so type 1a supernovae aren't the only type of so-called transient events that LSST will see in very large numbers. It'll see all sorts of exploding stars, flares on stars, the centers of galaxies accreting gas and flaring up. We'll see an awful lot of variable things over this 10-year survey. So here's a good plot. This one. So here's a plot that shows lots of different kinds of objects that we know about already, with their brightness increasing this way, so these are bright objects, and the duration of their explosion increasing this way. So very bright things that last 3 months are up here, faint things that only last a day are down here, and look at all this empty space for us to go exploring in. So we could ask questions like, well, what really happens when black holes collide? We know that they have this funny chirp that we can hear in gravitational wave detectors, but we don't know everything that's going on there. Maybe there's some light that comes out as well, and we won't know until we go look for it with LSST. Okay, so lots of explorations we can do with LSST. And clearly we've come a long way since the first explorers arrived in Tucson. I was reading about your city the other day and was pleased to see that next time I come, and I'm not busy at the Project and Community Workshop, there's a good place to visit. I don't know if any of you have been here to the Murray Springs Clovis site, but it's fun to think about the Clovis people arriving in the Tucson area something like 10,000 years ago. And here's some archaeologists working on a mammoth kill site. So we know something about the Clovis people. They used to eat mammoths. And from that, we know something about how they lived. They were hunter-gatherers. They used to hunt mammoths and gather berries and so on. And then at some point, they stopped doing that and started farming, maybe a few thousand years later. But I don't think they really stopped hunting and gathering. And the reason I think that is because I think we're still hunting and gathering. Here's this is from Germany, actually, this picture. This is a picture of a carving of a mammoth that dates from 35,000 years ago. So people like the Clovis people were not only hunting and killing mammoths, they were making art about the mammoths that they were hunting. So they were representing the things that they were hunting back to themselves. They were probably drawing maps for each other to show where to go hunting. All of which is to say that doing these explorations with LSST, if you ask, well, why do we do it? I said that it's because we're interested and because all of you are interested. Why are we interested? It's in our nature to be interested. At some level, we are still hunting and gathering. It's just we're hunting and gathering information these days rather than mammoths. So it's not just me and the professional scientists who will be doing explorations with LSST. All of you can too. So Ardis will maybe say a little bit more about this, but I'm interested in doing science with not only professional scientists, but also so-called citizen scientists. Anyone can take part in science because you all have the intrinsic ability to be a scientist. You're all explorers, all hunters and gatherers. And so here's a website you might like to check out later. It's called spaceswaps.org. And at this site, you can help me find new gravitational lenses in images that are rather like the LSST ones, taken with the Hyper-Supreme Cam, but similar image quality, similar depth. Come and help me find gravitational lenses. The project that we're running, the SpaceWarp site, was actually made by a colleague of mine in Oxford using a tool called the Project Builder, provided by the Zooniverse that hosts these projects. This is a tool that allows any scientist, any professional scientist, to design a project and put it together, put the data in it that they want to explore, and then make it available to the citizen scientists out there. So LSST will do the same. It will use the same technology to enable, let's say, possibly hundreds of explorations to be done with citizens like yourselves. Okay, so I hope I've shown you something of how LSST will provide many different maps for others to follow, lots of data to explore. And so now I'm going to hand over to Ardis, who's going to show you some other kinds of exploration that LSST will enable.
Good evening, everyone. 150 years ago, in our great state of Arizona, John Wesley Powell was the first explorer to successfully navigate the Grand Canyon. He did it because he was interested in geology. He believed that going through the canyon, which, by the way, others said could not happen, he could read the story of the rocks in the layers. But in doing this, he also made a map. He made a map of the route, he measured the altitude of the canyon cliffs, and documented many discoveries along the way. In his book, which was a journal of his trip, The Exploration of the Colorado River and Its Canyons, he tells a particular story that I'd like to recount to you. He talks about a time when he was climbing a vertical cliff, which he often did because they used barometers to measure the top of the cliff to the bottom of the river to figure out the altitude of the cliff, or the height of the cliff. He got to a point where he couldn't reach a foothold or a handhold. And so he called to one of his crew, Bradley, who scrambled up to a rock above him and tried to reach him, but he couldn't do it. He looked around for rocks or sticks or brush, and there was nothing there. Powell had a barometer strapped to his back, and Bradley suggested that he used a barometer case as a way to extend a reach. But the case was very slippery, and Powell only had one arm, having lost the other one in the Civil War. So he didn't want to do that either. But he was losing his grip, having hung there for quite a long while. Bradley finally came up with an idea that worked. He took off his pants and he lowered them down, and Powell was able to grab them and be pulled to safety. And I bring this story up to you because I want to talk to you a little bit about the benefits of exploration. So Phil talked to you a little bit about why we explore. We are wired to explore. It's an emotional need we have. But I will tell you that exploration really improves us, not only as people, but as a society. It breeds inventiveness, and inventiveness develops our critical thinking skills. It also helps us learn new things, and learning new things helps improve our worldview, helps put things into context for us. And finally, every explorer I've ever read about does it because they want to make their mark, they want to tell their story or build their monument. Haven't you ever done an exploration like that? But it doesn't end with just doing it. You want to come back and share it, don't you? And so telling your story of the exploration develops your communication skills. And I think these are all excellent reasons why we, no matter what our age, should continue to explore. In the first week of operations, LSST will collect more data than Hubble ever has. Can you imagine that? How do you make sense of all of that? How do you make context for it? That's really what our charge is as education and public outreach, is to develop those maps, to develop those routes for people to follow, so that we can explore with some sort of idea in mind, some sort of tools in hand. I think it's a really excellent way to think about our mission, in fact, that we're developing pathways for all of you to explore, no matter what your age or state of life. It was only 90 years ago that galaxies were actually invented as a concept. And the story of how that happened was astronomers saw all these symmetrical gas clouds in space, kind of like pinwheels, and they called them spiral nebulae. And actually in this quiz I was going to show a picture of an early sketch of one of these spiral nebulae. And at the time we thought that these spiral nebulae were part of our own galaxy, the Milky Way. Henrietta Leavitt, which you see here on the left, discovered a particular relationship with a certain type of star called a Cepheid variable. She found out that if you measured the time period it took for these variable stars to brighten and then dim, it was correlated with how far away they were. And so these variable stars became a sort of standard candle, like Phil was talking to you about a few minutes ago. And with them, astronomers could measure distances in the universe. This Hubble Space Telescope picture images the very first standard candle variable star that Edwin Hubble found about 15 years later in the Andromeda Galaxy. And with that, he realized that this galaxy, this island universe, was not part of our own Milky Way, but it was much, much farther away. And in just a short amount of time, that greatly expanded our view of how large space was, how large the universe was. That was only 90 years ago, so think about that. What's going to happen in the next 90 years? By comparison, let's look at technology. The picture on the left is one of Hubble's original plates from 1923. He used a 100-inch telescope, and he exposed that plate for 40 minutes. The picture on the right is a picture I took with my telescope here in Tucson, 14-minute exposure. So not only is our knowledge of astronomy expanding, but our technology is. And it's because the technology drives the science and the science drives the technology. There's a synergy between them. We want to know something, so we have to develop a tool to do it. We have the tool developed, and we gain new knowledge from it. Phil is a professional astronomer. And of course, they're all wildly excited about LSST. But I'm here to tell you how you can get in the game too. Because I will assert that astronomy, like baseball, can be played in a lot of different ways. So in fact, that's sort of our mission in EPO, right? It's to bring the game to you in whatever capacity you'd like to play it. So let's start with the rec leagues. For the education and public outreach effort here, we're working with science centers and planetaria to develop rich multimedia products that can be used to tell the story of LSST and its many discoveries. There's a space for amateur astronomers here too. Imagine that you're an amateur here and you have a specialty. Maybe you like to look for asteroids or comets. Maybe you're really interested in a certain type of variable star or supernova. We will have data that you can come and download and explore. And I will wager that it's probably more data than you've ever worked with before. Now, some people prefer to be not so actively involved, not so hands-on, but more sit on the sidelines and have things delivered to them. And there's a space for you, too. We're developing a tool called the Sky Viewer. Now, a lot of you probably have an app on your phone that looks sort of like this. You can hold it up to the sky, and you can find out what planet that is you're looking at, right? But this will be an entirely new sky to you. And the reason for that is LSST sees deep. It sees very faint objects. Objects so faint that they're beyond the reach of most amateur telescopes, even the brightest ones. So this is going to deliver an entirely new sky to you, one that you have not explored before, one that you're not familiar with. And how do you even make sense of all of that? Well, we're going to develop guided tours for you. So if there's a particular type of object you'd like, we can take you on a tour of some of our favorite objects like that. We'll give you links to new discoveries, unusual objects we find. That will, if you click on these things, they'll come back with pictures and news stories so you can make some sense of them. This is a tool I'm very excited about us developing. And finally, we're going to put a major emphasis on education, our students. And our audience for education are students from advanced middle school through college, because really, they're the same student in terms of level of sophistication, of what their background knowledge is. Their bodies are just different sizes. And so what we're going to be really focusing on in college are the non-science majors, the people who take astronomy as a general elective. But in high schools across the country, people take astronomy as part of earth science, individual astronomy courses, sometimes physics. And so there's a lot of opportunity for us to inject some of these avenues into the curricula, not only here, but also in Chile, where our telescope is being built. And by the way, all of our materials will be fully developed in Spanish as well as in English. So we're developing these investigations for students that are going to be highly interactive, where students can actually work with authentic data instead of simulations. And these investigations are arranged around 6 themes of science. Now, we selected these themes based on what is commonly taught in astronomy classes or curricula across the country, but also they play to the strengths of the LSST science data set. Within each of these themes, we'll develop several investigations. The heart of these investigations are what we call an online science notebook. Now, this is a relatively new technology to most people. An online notebook is a way for you to access and work with data with only a website, a browser. That's it. So you can do it from your house as well as your school. There's nothing to download. There's no special software to install. There's no permissions to get around firewalls. There's no bandwidth issues. Best of all, we have embedded tools that are going to do most of the heavy lifting for you. So the focus for the students and the researchers become thinking about the science instead of thinking about how to get to the science. And I'll give you an example of one of these tools in just a moment. Further, these notebooks will be customizable, so instructors can set them up any way they'd like. And they're going to come complete with class management tools, teacher guides, assessment materials aligned to the standards. So here's an example of our 6-filter mixing tool. And this mixing tool is from a notebook where we teach students about the 6 filters that the LSST telescope will have and why astronomers want those filters, what uses are for them. So to start with, we'll select a filter like the U filter. No hands. We can adjust the contrast and brightness, and then we can assign a color to that filter. We'll pick violet. We can proceed then and choose any filters we want. As we add each filter, we can again adjust it and assign a color to it. Now, in some instances, students might find a reason to build a full color 6-filter image. But in other applications, maybe only a few of these filters are really the best ones to use. So you can turn the filters on and off and build the image as you need to. At the end, you can save it, you can share it, and you've produced not only a pretty picture, but actually a science image that tells a story. And I think that's a very powerful tool. In fact, I think these tools will be one of the really, really powerful things that our students will use to do research on their own. Perhaps some amateurs will use these to do research, whether they're embedded in our notebooks or by themselves. The top prize for this year's International Science and Engineering Fair in Physics and Astronomy went to a high school student who did astronomy research with the Kepler Exoplanets database. So she, from her school or home, did all of this research using online data. And this is precisely what we're going to offer. So just imagine the possibilities for doing research with this a powerful database and this set of tools and notebooks that we'll develop. So there's a discovery space here, not only for students, but for interested amateurs. There's a place, in fact, for all of you in this game. So these are some of the pictures I was going to show you. These are the tools I began my teaching career with. When we did graphs, we actually had to use pencil and paper and rulers sometimes. Does anyone recognize that tool in the bottom left? Yeah, this is what we used before calculators. And this machine on the right, what we call a ditto machine. So if I wanted to make copies for my students, I'd make a master, and I'd put it in there, and I'd crank the number of times I needed to make copies. Or maybe some of you remember that wonderful smell of a freshly made ditto. So by the end of my career, things had changed a bit. Everything now is richly infused with technology. Learning can proceed at a faster and deeper pace. And we intend to develop tools that will match the agility of our technology and our students in our classrooms. We're enamored with the stars. Do you ever notice how they're just all over? Why is that? I wonder if you could help me with something. There's a word I'm missing here. So I'm going to say this, and could you fill in the word when I get to the right place? Twinkle, twinkle, little star, how I wonder what you are. I'm glad you didn't forget about wonder. I didn't forget about it either. I want to be filled with wonder and awe. I want to know new things. I want to be delighted by that newness. I want to find some better way to understand where we are in this cosmos. So what are we going to discover with LSST? Are there outer planets in our solar system that we haven't found yet? What's the fundamental nature of dark energy and dark matter? How did our galaxy form and evolve? What new objects that we don't even know about now will LSST discover? And what will we find out about them? So I invite you, no matter what your fan base is, what your involvement is, to find a way to chart your personal journey, your voyage, make your map, and get in the game. Thank you very much.